So welcome all. Today we are trying to learn something about distributed shared memory. So here for distributed shared memory, I am saying it is memory for all, which means we have different servers running separately, different processes which are running on different servers, and these processors actually they are using their own personal memory, whatever physical memory they have on their respective server. But let us assume we have a separate memory which is made available to these processes. Why it is needed? Because there is a limitation of physical memory. What happens in a single standalone system? When what you have a physical memory, it has a limitation of certain GB, like 4 GB, 8 GB, 16 GB, whatever GB, and after that you need to assign some virtual memory, like okay, there will be some paged virtual memory from where which will be accessed by the processes, and processor will not know that there is you are accessing a hard disk or any other device. Okay, process will understand like okay, your physical address space has enlarged. You know? So this shared memory, distributed shared memory, will also be something like that, where you will have your systems, servers, they will be working, and the processes working on these systems, they will assume that there is a part of physical memory which is being accessed by all the servers. Okay, so all the processes will assume that they are accessing their own physical memory. Definitely there will be a latency associated when they are accessing the physical memory on board and accessing the physical memory which is on a different board, but still this is something about a distributed shared memory. So basically what happens, this is a map where you can understand where you have different servers, and suppose these are the round circles, we are saying that it is a process. So processes which are executing, they will have their own physical memory. You can see these servers are having physical memory, right? At the same time they will also understand that the distributed shared memory which is not on board, but still they will assume that this is totally in the memory address space. Okay, so this is what you have to understand in distributed shared memory, that there is a memory which suppose there is a limitation of physical memory, it was of 16 GB, right? Suppose whatever limitation of the physical memory, and this distributed shared memory was something like 2 GB, 10 GB, 15 GB, 16 GB. So what happens here now? Your address space will be of 16 GB plus 16 GB, 32 GB, and this will happen for all the processes on the different servers, right? So this is what you have to understand in the distributed shared memory. Now what we say is, we call it Numa architecture. I should say Numa means non-uniform memory access. What happens in Numa is non-uniform, means what happens, they all have their physical memory. So with physical memory, this physical memory will be accessed in less time, and for accessing distributed this shared memory, it will take a little more time, right? So that is why it is non-uniform, right? But we are accessing the memory. This may happen not only with distributed memory, but this new architecture may happen with other multiprocessor systems as well. And what happens in a multiprocessor system, you would have seen like there are several processors, right? So definitely there will be somewhere a physical memory, and this physical memory will be accessible to all the processors. So what will happen? It may be nearer to some processor and farther from some processor. Okay, some part of the memory may also be like that, which can be nearer to a processor and farther to another. So in this way you can assume, you can understand that the memory access may be non-uniform. Similar is the case here, where you will have a physical memory and a shared memory, and this may become non-uniform, right? But still, the distributed system, you understand that we will have very high speed access kind of thing. We will try to connect with fiber optics kind of things for access, but still there will be some limitations, right? Now till now what we have understood, that there is a system. In the distributed system, these servers used to communicate with message passing, right? Now we are thinking about this distributed shared memory. What is it? Is it different from message passing, or it is same to it, or is there something that we have to discuss about this message passing versus this distributed shared memory? Whether they are same, they are different, what is the scenario, right? So let us start from here. Let us talk about the variables being marshaled, right? What happens, say, in while programming you create some variables, right? Now if you use this message passing scenario, what will happen? You will have to send the variable from one process to another, variable with the value to from one process to another. So you have one process P1 running on one server, you have a P2 running on a different server. You want to send this variable value from one server to another. What will you do? You will convert whatever the variable value here you have in a general format, okay, and you will transfer this format to the this place P2, and again from this general format it will be transferred to a format which is understandable to P2, right? This conversion will be called as marshalling, okay. So what happens at the sender side, the variables, these all the things can be marshaled, and on the receiver side it will be unmarshaled, right? So what happens here? In the message passing system, definitely we will need marshalling and unmarshalling and these kind of things. But if you will have a shared memory kind of thing, where you will keep the variable v1, this process P1 will write it, and this process P2 can read from here, right? So in that case you will not need a marshalling or unmarshalling kind of thing. So that is something that you can assume, whatever you say, benefit or not a benefit. But still, let me tell you, you had to do marshalling here, you need not do marshalling here. But think about a communication in a heterogeneous computer. You have a variable written in a particular format here, right? Now if the computers are of heterogeneous environment, means this is having a different format for storing the variable, this is having a different format of understanding this variable. In that case, what will happen? In this case, these heterogeneous computers will not be able to understand, complete their communication, right? So using DSM. But if they are using this marshalling, unmarshalling kind of thing, then what will happen? Then they can use it, then they can work nicely. How? It will marshal in a general format, and this also understands this general format. So from this general format, it can convert it in its own format, right? So this is something we have to understand. The other thing is default synchronization. So synchronization between processes is achieved in the message model through message passing, right? So whatever synchronization we want to achieve, we will transmit some information to the other process, and then we can achieve the synchronization, right? Suppose we have seen what happens in synchronization. We will keep on executing. We will keep a method here for sync, okay. It will also have sync, it will also have certain operations, and then it will have sync. Then what will happen? maybe we will have some number for synchronization. So it will execute these operations and wait here to execute all these operations, and then it will work, right? So in this way synchronization will work in message passing scenario. But when you will have this DSM, what will happen? You will have a memory, you will store the variable, so you will use certain things like semaphore or critical section kind of things, and in that way you will implement the this thing DSM, synchronization in DSM, right? Execute at same time. Okay, the thing is DSM can be made persistent. What happens in persistent means processes communicating via DSM may execute with non-overlapping time. See, you have this DSM, you have the variable v1, you have kept it here. What persistence means? They are different processes, P1, P2 and others. So P1 will write here, P2 wants to read from here. Okay, so P1 can write here and go for other work, or it may commit and it may say that, oh, our work is over. P2 can come at some different time and start using this variable v1, no problem. This can happen in DSM only. However, if you want to use message passing, then P1 will send the message to P2. At the same time, P2 should be active, running, executing to receive this message. है ना? So this is what we have to understand, that in message passing these two have to be running and executing at the same time. However, when we use DSM, it is persistent. One can keep the data, other can use at the overlapping time, right? So this is what we have to understand. So one thing that we have to understand is that message passing is a model, DSM is a model which can be used, keeping in mind that none of them we are claiming to be superior, right? So message passing is also a model. It has some advantage and disadvantage. DSM also will have some advantage and disadvantage. We are not claiming that one of them is preferable, okay, or especially we are not saying that DSM is preferable to message passing. However, DSM, as we are seeing, it has certain advantages. Variables are there. If we are able to perform synchronization and consistency, these kind of things, then it is better. One more thing that was in how it will execute in heterogeneous environment, marshalling is not required now. So keeping these things in mind, we have to understand that both of them have some advantage and disadvantage. We are not claiming DSM to be superior than other, right? Now, how will you implement these things? For implementing, you will need a hardware, a specialized hardware for this thing, which will allow you the load and store operation. So you have seen the cache memory modules in your systems. Similar modules can be used for this shared memory, no problem. The other thing is paged virtual memory. Actually, whatever your memory will be, whatever your hardware you are taking the memory should be paged, and the address should be given for each page. Size of the page may be something you will have to decide, but still you will need a paged virtual memory. Other thing is middleware. You will need a specialized solution software, means software module that will support distributed shared memory, right? Which will allow you implementing, sharing the data among different processes. Okay, processes make calls to this layer when they access data items in the DSM. then this layer will allow the access to the data items. So this is something about implementation issue. Okay, sorry. A structure. So what we are talking about the structure is we are trying to understand design and implementation issues related to this DSM, and the first thing that we are seeing is a structure. So here a DSM system is just such as a replication system. As we have seen in a replication system, the data objects are there which can be replicated at different servers for being accessed. Similarly, in this place also we will try to keep replicated data, replicated objects in different places for accesses to the corresponding processes. Suppose for one data 5 processes are trying to access, so we will try to make 5 different copies and store differently and allow access to the processes. So each process will work on their own copy, right? Now this structure can be byte oriented, object oriented, or immutable data, right? So what will happen in byte oriented? Here the memory will be accessed with I should say, means you can address according to byte as well. Okay, means byte addressable memory. So it can be something like definitely you can combine 4 byte, 2 bytes kind of things for pages, but if you desire to keep the page size to a byte, that can also be possible. So basically what you have to understand is the user or the process will be allowed to define their own structure of data. Okay, so here you are having a byte addressable memory. You can write or read operation. See you have a read operation, suppose read x and write the value a, write x, write the value a, okay, read the value a. So for these operations what you are going to understand is you can structure the variable a. Okay, this value is actually the bytes sequence of zeros ones to be stored in the memory. In object oriented, you understand there will be a structure. So the I should say the shared memory is structured as a collection of language level objects. So you will not have these simpler read write operations. You will have specialized read write operations which will allow you to read and write objects. Okay. Other thing is immutable data. Now what we are saying is you will not have a simple read write operation or object kind of thing. You will have a tuple kind of things. You will write certain thing like course is BTech. Okay, so you will store these values. Suppose something like it will be a string, this will be also a string. So you will have certain defined like okay, this will be course and BTech. Similarly, in this way you can actually store in the data. Okay, course is BTech. Okay, name is something. Okay, your age is something. In this way, if you want to store, you can store the data. So these are the ways you can store the data, and this is how it can be, the DSM can be structured. Now we are thinking about synchronization model. What happens, you can understand in a distributed synchronization the service, this distributed synchronization service needs to provide which individual familiar constructs such as, okay, sorry, synchronization we are talking. What happens, there may be certain things like suppose you have operation on A like A plus 1, operation of B like B plus 1. Okay, these are the two operations, Now suppose one process, there are several processes P1 and P2 and other processes as well. Suppose P1 and P2 both are executing these two operations at the same time. What will happen? Anything can happen. Suppose see initially A and B all were 0, suppose, then there is always something you have to understand. Either there will be P1 before P2 or P1 after P2, right? But in this way, if they are executing simultaneously, what will happen? It may happen that P1 has executed A, this first instruction, P2 has also executed A, and after that this thing means P2 has executed. So what happens? P1 has read initial 0 value and P2 read maybe written after this, or it has since it is a distributed system, so it may be having its own copy, so it may be also executing on the value 0. So you are having a 1 here, having a 1 here, having a for B it is 1 here and 1 here. But however, if you executed P1 and P2, what should happen? This should be in the last it should be 2 and 2, right? So for synchronization you can use locks or semaphore kind of things, so that what will happen when P1 will execute, it will lock the system that now only P1 can write these variables A and B. P2 will keep waiting until P1 frees these things, right? So such kind of a synchronization model can be used in DSM also. Now certain things we have to understand about consistency. What happens in consistency? We have to understand that if proper if the concurrency is there, right? So what can happen? This B variable is there, A variable is there, and these are being read or written by different kind of things, right? So not only write operations, suppose write operations are definitely changing the values, however read operations should also be consistent. Why? The whatever process P2 is reading a value for the variable A, it should be current value, should be currently the recent value, I should say, right? So we have to see these consistency models are certain things, and there is sequential consistency. What it says? It says that there are two rules. In the first rule it says that the read and write operations are there, it should be properly synchronized. What it says that if you are having a read operation on X and you have read a value A, then it should have come out of either a write operation on X, A, which is the most recent one, which is the most recent write operation on X, or it should be an initial read. Okay. The second thing is it says that it should be the order of operation. Okay. In this environment, the order, actually what will happen, B is being read by P1, P2 and others as well. So if you see the line how it operates, B is read for here also, A is read, kind of written right, these kind of things may happen. So there should be this order, should be in the order of processes. So this is something, order should be maintained. So this is how sequential consistency is there. Then there is something called coherence, is a consistency model where it says a little relaxing kind of thing. Suppose every process agrees on the other of see, it suppose write operations can be done on the same location. Okay, in the DSM you have a variable, one can write and other can also write. Okay, but they do not necessarily agree on the ordering of the write operation. Okay, that P1 will write first and P2 will write second. This is not order. So if this is not order, then this is a weak kind of consistency. However, this first rule is maintained, that whatever is read is the recently written thing. Okay. So this is something about coherence. Weak consistency is something which says that, okay, let us assume no other processes may access the data items accessed under this mutual exclusion kind of thing. Okay. So whenever you need a variable to be written, it will be given an exclusive lock, and it will use the semaphores and those kind of thing. It will write these things, and later on other can access it. So now the thing that you have to understand is updation, actually the write operation only, how it will be written. Actually we have understood that objects are there. Whenever one object is there, then the other processes which are executing, these processes will have the copies of these objects, right? So process P1, P2, P2 and so on, they will have different copies of these objects. Now what we can do, how can we perform the write operation? So in DSM we are having these two ways of writing operations. It can be write update or write invalidate. In write update, what we are saying is, whenever we are writing something, one process is writing something, so what we are doing, we will write it here, as well as we will immediately send a multicast message to all the processes to which can update their own objects. Okay, this is write update. So whenever it is written, it is updated, all the copies will be updated. This is write invalidate. In write invalidate, what will happen? Different copies are there. So one process, when they want to write, before that they will send a message to all of them that your these objects are being written, and since they are being written, what you need to do is invalidate your copies. Later on you can get the copy, the final one, after writing, but for now invalidate your copies, and now I am going to write this object. Okay, so this is write invalidate, which will write and make these things invalidate. So since these things will be invalidated, what will happen later on? They will have to get these objects from here, right? So there will be a large communication between these things. One thing we can understand, here is only one communication, here is at least 2 times communication, right? So next thing that we are going to see is granularity. Suppose you have paged virtual memory, right? So what happens, this is page, this is the nth page, this is n plus 1 page. Okay, from here this is n plus 1 page. Now you have 2 variables, you can see A as well as B. Okay, one process P1 is using variable A and one process P2 is using variable B. Now this is paged virtual memory. When you have to access, it will access the whole page. So now if P1 is trying to execute something on A, it is using this whole page, right? So it is using, although it is only using certain part of the page, okay, only it is executing on A, it is only changing the values on variable A, but still it is using the whole B. Now either this page can be replicated, suppose it was here as well, and B also has taken this page. Okay, so this P2 is also taken, so P2 is also having B as well as A. So now what will happen? Now whenever suppose what this thing is using A as well as B is also here, Now it is performing some updation in A. So in a way it has performed updation in this whole page. So wherever this page has been replicated somewhere, so what will happen? A message will go to all these things. If you are using this write-invalidate kind of thing, this this packet here will be invalidated. So although there is no need of invalidation because it is not working on A. So there should be a label of this thing, the page size, that the size should be like this. Page size can be restricted kind of thing, so that we can accommodate certain structure variables in a particular page, right? Sometimes it is also a case where we need a large page size. Why? Because in certain cases the pages need to be worked on if there are a small data part, if it has to execute on A, B, C, D and so on. So every time it will have to access the other things, so it will increase communication between process and memory, right? So false sharing is something when somebody needed just A and you are sharing the whole this thing, where B is also being shared. Actually B is not needed here for P1, but it has been shared with P1. So what happened? This is false sharing. So when it was false sharing? When it needed 2 or more processes share part of a page, right? So now 2 or more processes are sharing a part of page, but what happens? Only one in fact access each part. P1 is accessing A and P2 is accessing B. So it is false sharing. It is actually they are not sharing. It is working on a different thing and P2 is working on a different part of memory, but still they are sharing this memory. Okay, so it is false sharing. Now let us understand thrashing. Thrashing is nothing but you can understand what happens. Certain kind of you can see in DSM you have seen write invalidate kind of thing. So what will happen? Whenever you are updating a replica, you are sending invalidate message to all of them, right? So it will take much of the resources communicating for invalidation. So DSM runtime spends an inordinate amount of time invalidating and transferring shared data compared with the time spent of application processes. So thrashing you would have seen in operating system as well. What happens when you are not giving much time for processing and you are giving your time for this kind of works which is not that important as processing. In that case you call it as thrashing. So here it is thrashing. In operating system it was something like when you keep on swapping your processes from memory to the processor, and you are not actually doing processing, right? You are giving less time to processing and you are continuously swapping the processes. That was thrashing. So here also it is thrashing, right? So this is all something about this thing, this distributed shared memory, and you have also seen coherence, thrashing, and different models, granularity, synchronization, structure, hardware, these kind of things. So I'll go through the book also. Okay, thank you.